Close your eyes for just a moment. Breathe in deeply, and now look up. Even through your closed eyelids, you can imagine it, can't you? That vast, endless darkness scattered with points of light. Stars that have been burning for billions of years, their light traveling across incomprehensible distances just to reach your eyes in this single, fleeting moment. Welcome back to the Midnight Explorer, where we wander through the quiet corners of human curiosity, where we trace the stories written in starlight and whispered across centuries. Tonight, we're not going anywhere. Tonight, we're going everywhere. We're going to explore the sky, not the sky you see when you glance up during your evening walk, but the sky as humanity has seen it, wondered about it, feared it, mapped it, and ultimately fell in love with it across thousands upon thousands of years. This is the story of astronomy, but more than that, it's the story of us, of every human being who ever looked up and asked why and how and what does it mean. So settle in, pull your blanket a little closer, let the world grow quiet around you, and let's begin at the very beginning, when the universe itself was born in fire and light. Before there were telescopes, before there were charts and equations, before there was even language to describe what they were seeing, there were eyes, human eyes, looking up. Imagine, if you will, a night 40,000 years ago. Somewhere in what we now call Europe, a small group of humans huddles around a fire. The flames crackle and pop, sending sparks upward into the darkness like tiny, short-lived stars. One of them, let's imagine her, has finished eating. Her stomach is full. The fire is warm against her skin. And now, in this rare moment of peace, she leans back and looks up. The sky she sees is not the sky we see. There are no city lights to wash it out, no airplanes blinking across it, no satellites tracing their silent paths. The Milky Way stretches across the heavens like a river of light, so bright and so dense that she can see her shadow cast by starlight alone. She doesn't know what stars are. She doesn't know about nuclear fusion or light years or gravity, but she feels something, a sense of vastness, of mystery, of connection to something larger than herself. Maybe she points. Maybe she tries to make sense of the patterns she sees, that cluster of stars that looks almost like an animal, that bright one that seems to move differently from the others across the seasons. This moment, this simple act of looking up and wondering, this is where astronomy begins. Not in a laboratory, not in a university, but in the human heart, in that deep and ancient need to understand our place in the cosmos. The earliest humans were not scientists in the way we understand the term, but they were observers. They had to be. Their survival depended on it. They noticed that the sun rose and set, tracing a predictable path across the sky. They noticed that the moon changed shape, cycling from full to crescent and back again. They noticed that certain stars appeared in certain seasons, and they learned to use these patterns as a calendar. When those stars appeared, it was time to plant. When others rose, it was time to harvest. When still others dominated the sky, it was time to prepare for winter. The sky was their clock, their calendar, their guide. Archaeological evidence shows us just how deeply our ancestors engaged with the cosmos. In caves across Europe, Lascaux in France, Altamira in Spain, we find paintings that date back 15 to 20,000 years. Among the images of bison and horses, we find dots and patterns that some researchers believe represent star maps, the Pleiades cluster perhaps, or the constellation we now call Taurus. In what is now Scotland, there's a field called Warren Field. It doesn't look like much, just a series of pits in the ground. But archaeologists have determined that these pits, which date back 10,000 years, form a lunar calendar. 10,000 years ago. Before writing, before cities, before agriculture had fully taken hold. Already humanity was mapping the sky. But observation alone wasn't enough. The human mind does something unique. It creates stories. Look at the stars and you'll see dots of light. Look at them long enough, connect them in your imagination, and you'll see a hunter, a bear, a dragon, a swan. Every culture on Earth did this. They took the random scatter of stars and wove them into narratives that reflected their own world, their own beliefs, their own fears and hopes. The ancient Egyptians saw in the constellation Orion the figure of Osiris, god of the afterlife. When Orion rose before the sun in summer, it coincided with the annual flooding of the Nile, the event upon which all Egyptian civilization depended. The sky and the earth were connected, inseparable. The Aboriginal peoples of Australia, whose continuous culture stretches back perhaps 65,000 years, saw in the dark spaces between stars, what they called the dark constellations, the shape of an emu, of a serpent. Their stories connected the sky to the land, to the seasons, to the very dreaming that created the world. In ancient China, astronomers looked up and saw a celestial empire mirroring the earthly one. The emperor was the son of heaven, and events in the sky, comets, eclipses, unusual stellar configurations, were seen as omens, messages from the cosmic order about the state of the earthly realm. The Greeks, whose astronomical traditions would come to dominate Western thinking for millennia, saw heroes and monsters, gods and mortals, all immortalized in the stars. Perseus, who slew Medusa, Andromeda, the princess chained to a rock, Cassiopeia, the vain queen. These weren't just stories, they were a way of organizing the sky, of making it knowable, manageable, human. But here's what's beautiful, what's almost heartbreaking in its consistency. Despite the vast differences in culture, in language, in geography, nearly every ancient civilization looked at the sky and asked the same fundamental questions. Why does the sun rise and set? Why does the moon change shape? What are those wandering stars, the ones that don't stay fixed in place like the others? What causes an eclipse, that terrifying moment when the sun is devoured by shadow? And perhaps most importantly, what does it all mean for us down here on Earth? These questions were not academic exercises. They were deeply practical, deeply spiritual, deeply human. The answers they came up with, the mythologies, the calendars, the careful observations passed down through generations, these were humanity's first attempts at astronomy. And they worked. They worked well enough that civilizations rose and flourished, guided by their understanding of the sky. But there were some people, in some places, who wanted more than stories. They wanted to measure, to predict, to truly understand the mechanisms behind the celestial dance they witnessed every night. And it's here, in the ancient world, that astronomy begins to transform from mythology into something else, something closer to what we would recognize as science. Let's travel now to ancient Mesopotamia, to the land between two rivers, where some of the first cities in human history rose from the alluvial plains. Babylon, Nineveh, names that echo across millennia. It's around 1800 BCE, and the night sky over Babylon is clear and brilliant. On the roof of a ziggurat, those massive stepped pyramids that dominated the Mesopotamian skyline, a priest astronomer sits with his clay tablet and stylus. He's not here to pray, though his work is considered sacred. He's here to watch, to record, to track. The Babylonians were perhaps the most systematic of all ancient astronomers. Night after night, year after year, generation after generation, they watched the sky and wrote down what they saw. Not stories, not myths, numbers, positions, patterns. They tracked Venus with obsessive precision, noting its appearance and disappearance, its position relative to other stars. They tracked the moon through all its phases, noting not just the major transitions, but the subtle variations in its cycle. They tracked the sun's path through the zodiac, that band of constellations through which the sun, moon, and planets all move. And after centuries of observations, something remarkable happened. They began to notice patterns, cycles, predictability in the heavens. The Babylonians discovered something profound. The sky wasn't chaos, it was order. They found that eclipses, those terrifying events when the sun or moon darken, weren't random. They followed a pattern, a cycle that repeated every 18 years, 11 days, and 8 hours. We call it the Saros cycle today, though they had their own name for it. This was revolutionary. If eclipses were predictable, then they weren't divine omens in the way people had thought. They were natural phenomena, governed by rules, by patterns that human minds could comprehend and predict. Imagine the power this gave them, to know years in advance when an eclipse would occur, to stand before a king and say with confidence, "On this day, in this month, the moon will be devoured by shadow, and then it will return." And to be right. The Babylonians developed sophisticated mathematical models to predict the positions of the planets. They divided the sky into sections of 30 degrees each, creating the zodiac that we still reference today. They tracked what they called the white star, Venus, the red star, Mars, the yellow star, Jupiter, and others, noting with painstaking care their movements against the background stars. These weren't primitive people making lucky guesses. This was sophisticated, systematic science. Their observations were so accurate that modern astronomers working backward from computer simulations have verified the Babylonian records. They were off by mere fractions of a degree. Astonishing accuracy achieved with nothing but the naked eye, patience, and centuries of accumulated knowledge. Now let's shift westward to the sun-drenched islands and peninsulas of ancient Greece, where astronomy was about to take another leap forward. It's around 600 BCE, and in the city of Milos, on the coast of what is now Turkey, a man named Thales is making a bold claim. He says that water is the fundamental substance of all things. He's wrong about that, but he's right about something more important. He insists that natural phenomena have natural causes, not supernatural ones. This might not sound revolutionary to us, living in a scientific age, but at the time it was radical. It meant that the universe could be understood through reason, through observation, through logic, not through mythology or divine revelation alone. Thales reportedly predicted a solar eclipse in 585 BCE. Whether he actually did this or whether it's a legend embellished over time, we can't be certain. But the story tells us something important about how the Greeks saw astronomy, as a field where human intelligence could penetrate the mysteries of the cosmos. The Greeks inherited much from the Babylonians, their observations, their mathematical models, their star catalogs, but they added something new. They asked not just what and when, but why and how. Pythagoras, famous for his theorem about right triangles, proposed that the Earth was a sphere, not a flat disk. His reasoning was philosophical. He believed that the sphere was the perfect shape, and therefore the gods would make the Earth spherical, but his conclusion was correct. Aristotle, that towering intellect of the ancient world, provided observational evidence for a spherical Earth. He noted that during a lunar eclipse, the shadow of the Earth on the moon was always curved, regardless of the angle. Only a sphere casts a round shadow from every direction. He also noted that as you travel north or south, different stars appear and disappear from view, something that only makes sense on a curved surface. But perhaps the greatest of the ancient Greek astronomers, certainly the most influential, was a man named Claudius Ptolemy, who lived in Alexandria, Egypt in the 2nd century CE. Alexandria. Just saying the name conjures images of learning, of the great library, of a crossroads where the knowledge of Egypt, Greece, Persia, and India all mingled and merged. Ptolemy was a mathematician, a geographer, and an astronomer. His great work, which we know by its Arabic name, the Almagest, was essentially an encyclopedia of astronomical knowledge, synthesizing centuries of observations and theory. At the heart of Ptolemy's system was an idea that seems obvious if you just look at the sky. The Earth is at the center of the universe, and everything else, the sun, the moon, the planets, the stars, revolves around us. This geocentric model, as we call it now, wasn't just arrogance or anthropocentrism, it was based on observation and common sense. After all, the Earth doesn't feel like it's moving. We don't feel any wind or motion from spinning at 1,000 miles an hour. When you drop something, it falls straight down, not at an angle as it would if the Earth was rushing through space. The stars don't shift in their positions throughout the year in the way they would if we were orbiting the sun, or at least not in a way the ancients could detect with their instruments. And most importantly, when you look up, you see the sun and moon and stars moving across the sky. The evidence of your senses says clearly that the heavens revolve around the Earth. But there was a problem. Several problems, actually. The planets, those wandering stars, didn't move in simple circles. Sometimes they moved forward through the constellations, sometimes they slowed down, sometimes they appeared to move backward, what we call retrograde motion, and sometimes they changed brightness. To explain this, Ptolemy developed a system of breathtaking complexity and ingenuity. He proposed that planets didn't move in simple circles around the Earth. Instead, they moved in smaller circles called epicycles, which themselves moved along larger circles called deferents. Imagine a child sitting on a carousel at a playground. The carousel itself is rotating, but the child is also spinning on their seat. From the perspective of someone standing still, the child's motion would trace out a complex looped pattern. That's essentially what Ptolemy proposed for the planets. To make the model match observations even more closely, he added more complexity, points called equants, from which the motion appeared uniform even though the actual motion varied in speed. It was elaborate, it was complicated, but it worked. You could use Ptolemy's model to predict where a planet would be in the sky on a given night, and you'd be reasonably close to correct. The Almagest would dominate astronomical thinking for nearly 1,500 years. 15 centuries, during which Ptolemy's geocentric universe was simply how educated people understood the cosmos. It would take a revolution, one of the greatest intellectual revolutions in human history, to overthrow it. But before we get to that revolution, we need to journey to other parts of the world, where other astronomers were making their own discoveries, building their own understanding of the sky. While Europe entered what we often call the Dark Ages, the torch of astronomical knowledge burned bright in the Islamic world. From Spain to Persia, from Baghdad to Damascus, Muslim astronomers preserved the ancient Greek texts, translated them into Arabic, corrected their errors, and extended their insights. The House of Wisdom in Baghdad, established in the early 9th century, was perhaps the greatest center of learning in the world at that time. Here, scholars translated not just Greek works, but also texts from India and Persia, synthesizing knowledge from multiple traditions. Muslim astronomers didn't just preserve, they innovated. They built observatories equipped with instruments of unprecedented precision. Massive quadrants and sextants, carefully divided into degrees and minutes of arc, allowing measurements accurate to within fractions of a degree. They compiled new star catalogs, more extensive and more accurate than Ptolemy's. They refined the mathematical models of planetary motion. They developed trigonometry as a sophisticated mathematical tool for solving astronomical problems. The impetus for much of this work was religious. Islam requires that prayers be performed 5 times a day, facing toward Mecca. But how do you determine the direction to Mecca when you're in Spain or India? How do you determine the correct times for prayer? You need astronomy, you need mathematics, you need careful observation and calculation. So religious devotion drove scientific inquiry, and in the process, these astronomers made discoveries that would echo through the centuries. Al-Battani, working in the late 9th and early 10th centuries, produced some of the most accurate observations of his time. He determined the length of the solar year to within minutes of the modern value. He improved upon Ptolemy's value for the precession of the equinoxes, that slow wobble in Earth's axis that shifts the position of stars over thousands of years. Ibn Yunus in 10th century Egypt compiled massive tables of astronomical calculations that were used for centuries. His observations of eclipses were so precise that modern astronomers use them to study the long-term behavior of the Earth's rotation. Al-Sufi, in his Book of Fixed Stars, cataloged over 1,000 stars, describing their positions, magnitudes, and colors. He made the first recorded observation of the Andromeda galaxy, describing it as a small cloud near the constellation Andromeda. He couldn't have known that he was seeing an island of hundreds of billions of stars, over 2 million light-years away, but he saw it, and he recorded it. On the other side of the world, Chinese astronomers were conducting their own systematic observations, continuing a tradition that stretched back thousands of years. The Chinese had a different approach to astronomy than either the Greeks or the Arabs. They were less interested in developing geometrical models of the cosmos and more focused on careful, continuous observation and record-keeping. And their records were extraordinary. Chinese astronomers documented supernovae, those stellar explosions that briefly outshine entire galaxies, going back to at least 185 CE. The famous supernova of 1054, which created the Crab Nebula, was recorded in meticulous detail by Chinese and Arab astronomers, while it was apparently missed or ignored in Europe. They tracked comets, carefully noting their appearance, path, and duration. They recorded sunspots, dark patches on the sun's surface, over 1,000 years before European astronomers accepted that the sun could be anything less than perfect and unblemished. Chinese astronomers understood that eclipses were caused by the alignment of the sun, moon, and earth. They could predict them with reasonable accuracy. They tracked the precession of the equinoxes. They measured the length of the year to within seconds of the modern value. Their motivation, like so much of ancient astronomy, was a mixture of the practical and the spiritual. The emperor was the son of heaven, and the state of the heavens reflected the state of his rule. An unexpected comet, an eclipse occurring at the wrong time, unusual stellar phenomena, these could be interpreted as signs of heaven's displeasure, potentially threatening the legitimacy of the ruling dynasty. So the astronomer's job was not just to observe, but to advise, to interpret, to help the emperor maintain harmony between heaven and earth. Meanwhile, across the Pacific Ocean, in Mesoamerica, cultures were developing their own sophisticated astronomical traditions entirely independent of the Old World. The Maya, in particular, were among the most skilled astronomers in the pre-modern world. Without metal tools, without telescopes, without even the wheel, the Maya built observatories and tracked the movements of celestial objects with astonishing precision. They were particularly focused on Venus, which played a central role in their mythology and calendar. Maya astronomers tracked Venus through its complete cycle, 584 days from one evening star appearance to the next, with an accuracy that differs from the modern value by only 2 hours over 500 years. 2 hours over 500 years, achieved through patient observation with the naked eye. The Maya developed multiple interlocking calendars, a 260-day ritual calendar, a 365-day solar calendar, and a long count that tracked days from a mythological starting point. These calendars were so sophisticated and so important to Maya culture that they weren't just astronomical tools, they were the framework around which the entire civilization was organized. When the Spanish conquistadors arrived in the 16th century, they found books, codices, filled with astronomical tables and calculations. Tragically, most of these were burned by Spanish priests who saw them as pagan witchcraft. Only 4 Maya codices survived, and we're still working to fully understand them. But the stone monuments remain, buildings aligned to the rising sun on the solstices, windows and doorways that frame important celestial events, the remnants of a civilization that looked to the sky and saw order, meaning, and the very structure of time. Take a moment now. Breathe. Think about what we've journeyed through so far, from the first humans looking up in wonder, to the Babylonians tracking planetary positions on clay tablets, to Greek philosophers reasoning about the shape of the earth, to Islamic scholars refining the mathematics of the heavens, to Chinese astronomers keeping meticulous records, to Maya building stone observatories in the jungle. All of them separated by oceans and mountains and thousands of miles, united by a common human impulse to understand the sky. They didn't have our tools, our technology, our accumulated knowledge, but they had patience, they had curiosity, they had the willingness to observe, to record, to pass knowledge from one generation to the next, building layer upon layer of understanding. They got so much right: the length of the year, the cycles of the moon, the patterns of the planets, the predictability of eclipses. And yet, they were wrong about something fundamental, something so basic that overturning it would shake the very foundations of how humans understood their place in the universe. They were wrong about where we stood in the cosmic order. The Earth was not the center. And the man who would prove this, a quiet Polish astronomer in the early 15th century, was about to change everything. Frombork, a small town on the Baltic coast of Poland, cold in winter, misty and gray for much of the year, far from the centers of learning and power in Renaissance Europe. An unlikely place for a revolution. But in the cathedral here, in a tower overlooking the cold waters of the Vistula Lagoon, a canon named Nicholas Copernicus spent his nights observing the sky and his days working on a manuscript that would, quite literally, move the earth. Copernicus was not a radical by temperament. He was a church official, a physician, an administrator, conservative in his dress, his habits, his lifestyle. He had no desire to overturn the established order or to challenge church doctrine. But he had a problem. Actually, everyone had a problem, though most people didn't know it. Ptolemy's system, for all its mathematical elegance, had grown increasingly unwieldy over the centuries. To make it match observations, astronomers had to keep adding more epicycles, more correction factors, more complexity. The calendar was drifting out of sync with the seasons, a problem of practical importance to the church, which needed to calculate the correct date for Easter. The planets sometimes deviated from their predicted positions. Copernicus was trained in the Ptolemaic system. He knew it inside and out. But something about it bothered him. Not because it didn't work, it worked well enough, but because it felt wrong, inelegant, overly complicated. There's a principle in scientific thinking, often called Occam's razor. When you have two explanations that both fit the facts, prefer the simpler one. Ptolemy's system had become anything but simple. So Copernicus asked himself a question that seemed, on its face, absurd. What if the Earth isn't at the center? What if, instead of the sun circling the Earth circles the sun? What if the Earth is not stationary but spinning on its axis, completing one rotation every 24 hours? That would explain the apparent motion of the stars across the night sky. What if the Earth orbits the sun along with the other planets? That would explain the complex retrograde motion of the planets. It's not that they're actually moving backward, but that we're observing them from a moving platform, creating an optical illusion. Copernicus worked out the mathematics, and something remarkable happened. The model simplified. You didn't need epicycles upon epicycles. You didn't need equants and deferents and correction factors piled on correction factors. The motions of the planets made sense as a natural consequence of everything orbiting the sun at different speeds. Mercury, closest to the sun, zips around in just 88 days. Venus takes 225 days. Earth takes 365. Mars takes 687. Saturn, at the edge of what was then the known solar system, takes nearly 30. When Earth overtakes Mars in its orbit, Mars appears to move backward against the background stars. Not because it is moving backward, but because of our changing perspective. Like passing a slower car on the highway and watching it appear to drift backward relative to distant mountains. It was elegant. It was simple. It worked. But Copernicus was afraid. He wasn't just proposing a new mathematical model. He was saying that the Earth moves, that we're not at the center of creation, but orbiting around the sun like any other planet. This contradicted common sense. It contradicted Scripture, or at least certain interpretations of Scripture, passages that spoke of the sun standing still, of the Earth being immovable, established forever. It meant that humans, and the Earth they lived on, were not the focal point of God's creation. We were one planet among several, orbiting a star that might be one among many. For decades, Copernicus kept his ideas mostly to himself. He shared them with friends, circulated a brief manuscript in limited copies, but published nothing formally. It wasn't until he was on his deathbed in 1543 that his full work, De Revolutionissimus Orbium Celestium, on the revolutions of the heavenly spheres, finally saw print. Legend says that a printed copy was placed in his hands on the very day he died, May 24, 1543. Whether he was conscious enough to comprehend what he was holding, we don't know. But his book was out in the world, and the world would never be quite the same. Except it wasn't an immediate revolution. The reaction to Copernicus's book was initially fairly muted. Some scholars found it interesting, others dismissed it as a useful mathematical tool, but not a description of reality. The preface to the book, written not by Copernicus but a well-meaning colleague, even suggested the heliocentric model should be taken as a mathematical convenience, not as a physical truth. Many objections to the Copernican system were entirely reasonable given the knowledge of the time. If the Earth is spinning at 1,000 miles an hour, why don't we feel it? Why aren't we thrown off into space? If the Earth is orbiting the Sun, then our position relative to the stars should change throughout the year, creating what's called stellar parallax. Nearby stars should appear to shift position relative to more distant stars, but no such shift could be detected. How could the massive Earth be moving through space without any sensation of motion? These weren't foolish objections. They were good scientific questions, and Copernicus didn't have fully satisfying answers to them. The true answer to the parallax problem is that stars are so phenomenally distant that the parallax shift is too small to detect with telescopes far more powerful than anything available in the 16th century. But without that knowledge, the absence of observable parallax was a legitimate argument against a moving Earth. So, for decades, the Copernican system remained a minority view, a controversial hypothesis that some found mathematically interesting, but most didn't accept as physical reality. It would take new observations, new evidence, and new champions to turn the Copernican hypothesis into a revolution. Middelburg, Netherlands. A spectacle maker named Hans Lippershey is working in his shop, grinding and polishing lenses for eyeglasses. According to legend, and it may be only legend, his children are playing with some of the lenses, holding them up at various distances and angles. And at some point, they notice something remarkable. When you hold two lenses at just the right distance apart and look through them, distant objects appear closer. The church steeple down the street seems to leap forward, details suddenly visible that should be too far away to see. Lippershey recognizes the potential and tries to patent the device. He's not successful. The design is too simple, too easily replicated. Within months, spy glasses and perspectives, as they're called, are being manufactured across Europe. They're toys mostly, novelties, useful perhaps for military purposes, for spotting enemy ships at sea, but hardly anyone thinks to point one at the sky. Hardly anyone except a mathematics professor in Padua, Italy, named Galileo Galilei. Galileo is 45 years old in 1609. He's an accomplished mathematician and natural philosopher, known for his work on motion and mechanics. When he hears about the Dutch spyglasses, he immediately grasps the principle and builds his own improved version. His first telescope magnifies objects about 3 times. Useful, but still limited. He refines the design, 9 times magnification. Better, but still limited. By the end of 1609, Galileo has built a telescope that magnifies objects 20 times. And on a clear night, he points it upward. And he sees everything. Everything changes. First, the moon. To the naked eye, the moon appears as a smooth, glowing disk, perhaps with some vague darker and lighter regions. In Ptolemy and Aristotelian philosophy, the moon, like all celestial objects, was supposed to be perfect, unblemished, made of a pure, crystalline substance unlike anything on Earth. Through Galileo's telescope, the moon was revealed as a world with mountains and valleys, with shadows that lengthened and shortened as the sun moved across its sky, with highlands and what appeared to be seas. They're not actually seas, but Galileo couldn't have known that. The moon was a place, a physical place, with topography, with features you could map. Not a perfect celestial sphere, but something almost earthly. Galileo sketched what he saw, creating the first detailed maps of the lunar surface. Centuries later, when humans finally walked on the moon, they would visit some of the features Galileo had first drawn. Then, the stars. The Milky Way, that luminous band across the sky, had been a mystery for millennia. Aristotle thought it was atmospheric, perhaps exhalations from the Earth catching the light of the sun. Others thought it might be millions of distant stars, but that seemed impossible to prove. Through the telescope, the Milky Way dissolved into countless individual stars.
stars too faint and too numerous for the naked eye to distinguish, but clearly visible when magnified. The Milky Way wasn't a glow or a cloud. It was stars, uncountably many stars. And this raised a question. If there were so many stars invisible to the naked eye, how many more might there be? How vast was the universe? Then, Jupiter. On January 7, 1610, Galileo turned his telescope to Jupiter, the bright, wandering star known since antiquity. Near Jupiter, he saw 3 small stars, arranged in a line on either side of the planet. He thought little of it first, just a chance alignment. But the next night, they had moved. All 3 were now on the same side of Jupiter. The next night, they'd moved again, and now there seemed to be 4 of them, not 3. Galileo observed Jupiter night after night, and the pattern became undeniable. These weren't background stars. They were orbiting Jupiter. They were moons. 4 moons circling Jupiter just as the moon circles Earth. This was revolutionary for a simple reason. It proved that not everything in the universe orbits the Earth. Here was Jupiter with its own miniature solar system, a world with satellites, just as the Copernican theory said Earth was a world with a satellite orbiting the sun. The geocentric universe couldn't explain this. The Ptolemaic system had no mechanism for moons orbiting a planet that was itself orbiting Earth. But the Copernican system could. If Earth was a planet orbiting the sun, there was no reason another planet couldn't have moons. Then, Venus. Through the telescope, Venus showed phases like the moon. Sometimes it appeared as a crescent, sometimes nearly full, and its apparent size changed dramatically. This was the final blow to the Ptolemaic system. In Ptolemy's model, Venus orbits the Earth on a path that always keeps it roughly between us and the sun. In that model, we should only ever see Venus in crescent phases. We should never see it nearly full with the sun behind us from our perspective. But Galileo did see Venus nearly full, which meant Venus must orbit the sun, not the Earth, sometimes passing on the far side of the sun from our perspective. The observations were clear. The mathematics were clear. Venus orbits the sun. And if Venus does, why not Earth? In March 1610, Galileo published his observations in a short book called Sidereus Nuncius, the Starry Messenger. It was a sensation. Within a week, the first edition sold out. It was translated, reprinted, discussed in courts and universities across Europe. Some people were thrilled. This was exploration, discovery, a new world, new worlds revealed by human ingenuity. Others were troubled. If Aristotle and Ptolemy were wrong about the moon, about Jupiter, about Venus, what else might they be wrong about? How much of the established philosophy and theology, built on the assumption of a geocentric universe, would need to be revised? And some people simply didn't believe it. The telescope must be creating illusions, they said. It might work well enough for viewing distant ships, but the heavens were a different matter. Some scholars refused to even look through the telescope, convinced that it would only deceive them. Galileo himself was confident, perhaps too confident. He wrote mockingly of those who refused to accept the evidence. He entered into disputes with other philosophers and astronomers. He was brilliant, but not always diplomatic. And he was about to collide with an institution that did not take kindly to having its cosmology challenged, the Catholic Church.
Rome, 1616. Galileo has been summoned before Cardinal Robert Bellarmine, one of the most powerful theologians in the Catholic Church. The issue, Galileo's advocacy for the Copernican system. His insistence that the Earth really does move around the sun, that this is not just a mathematical model, but physical reality. The Church's position is complex. It's not that Church officials are necessarily opposed to the Copernican model as a mathematical tool. Many are quite sophisticated in their understanding of astronomy. But to assert it as physical truth seems to contradict Scripture. Psalm 93:1, "The world is firmly established, it cannot be moved." Joshua 10:13, "The sun stopped in the middle of the sky and delayed going down about a full day." If the Bible says the earth is fixed and the sun moves, how can the Church accept a cosmology that says the opposite? Bellarmine's position is essentially this. If Galileo can prove beyond doubt that the Earth moves, then the Church will reinterpret the relevant scripture passages as metaphorical rather than literal. But without definitive proof, the Church will maintain its traditional interpretation. And Galileo can't provide definitive proof. He has strong evidence, the phases of Venus, the moons of Jupiter, the mountains on the moon, but he doesn't have direct proof that the Earth moves. He doesn't have stellar parallax, which would demonstrate that Earth's orbit changes our perspective on the stars. He doesn't have a physical explanation for why we don't feel the Earth's motion. He has a better theory, a more elegant model, compelling evidence, but not absolute proof. Galileo is admonished by the Church. He is instructed not to hold or defend the Copernican theory as physical reality. He can discuss it as a hypothesis, as a mathematical model, but not assert it as truth. Galileo agrees, or seems to. He returns to Florence, where he's the court mathematician to the Grand Duke of Tuscany. For several years, he works on other topics. He studies comets. He continues his work on motion and mechanics. He avoids direct confrontation over cosmology. But he can't let it go. The evidence is too strong, the truth, as he sees it, too important. In 1623, a new pope is elected, Urban VIII, who had been Cardinal Maffeo Barberini. Urban is educated, cultured, interested in science. He and Galileo have been friendly. Galileo sees an opportunity. Urban gives Galileo permission to write a book about cosmology, with the caveat that it must present both the Ptolemaic and Copernican systems objectively, without advocating for either as absolute truth. Galileo sets to work, and in 1632 he publishes Dialogue concerning the two chief world systems. The dialogue is written as a conversation among three characters over 4 days. Salviati, who presents Copernican arguments and clearly represents Galileo's own views. Simplicio, who defends the Aristotelian Ptolemaic system and whose name unfortunately suggests simpleton. And Sagredo, an intelligent, neutral observer who, by the end, is clearly convinced by Salviati's Copernican arguments. The book is brilliant. It's clear, it's compelling, it's accessible to educated readers who aren't specialists in astronomy. But it's also not remotely objective. Simplicio's arguments are presented as weak and easily refuted. Salviati's arguments are given the best possible exposition, and in a particularly ill-advised move, Galileo puts one of Pope Urban's favorite arguments, that God, in his omnipotence, could produce any effect by infinite means, so we can never be absolutely certain of any physical explanation, into the mouth of Simplicio. Urban is furious. He feels mocked, betrayed. Galileo has crossed a line. In 1633, Galileo, now 69 years old and in poor health, is summoned to Rome to stand trial before the Inquisition. The charge? Suspicion of heresy, specifically teaching that the earth moves and the sun is stationary, contrary to Scripture and the Church's previous admonishment. Galileo tries to defend himself. He argues that he was only presenting both views, as the Pope had permitted. He argues that his intention was never to contradict Scripture, only to discuss mathematical models. But the dialogue speaks for itself. Anyone reading it can see which side Galileo favors. The trial is not really in doubt. The Inquisition has the power, and Galileo has neither political protection, the Grand Duke of Tuscany stays carefully neutral, nor the definitive physical proof that might change minds. On June 22, 1633, Galileo is found vehemently suspect of heresy. He is forced to kneel and read a prepared statement of abjuration. I, Galileo Galilei, have been judged vehemently suspect of heresy. I abjure, curse, and detest the errors and heresies of believing that the sun is the center of the world and immovable, and that the earth is not the center and moves. Legend says that after recanting, Galileo muttered under his breath, "Eppur si muove," and yet it moves. It's a wonderful story, the defiant scientist forced to deny the truth, but still asserting it in whisper, knowing that facts don't care about institutional power. But the truth is almost certainly apocryphal. It doesn't appear in any contemporary accounts. It emerges in books written more than a century later.
The truth is probably less dramatic and more human. Galileo, elderly and threatened with torture and imprisonment, said what he needed to say to survive. He recanted. He was sentenced to house arrest for the remainder of his life. The dialogue was banned. He was forbidden from publishing on topics of cosmology. He returned to his villa in Arceti, near Florence, where he would spend the next 9 years. His health declined. He went blind. His daughter, Sister Maria Celeste, who had been his closest companion and correspondent, died in 1634, leaving him devastated. But even under house arrest, even blind, Galileo continued to work. He compiled his earlier research on motion and material science into a new book, Discourses and Mathematical Demonstrations Relating to Two New Sciences, which was smuggled out of Italy and published in the Netherlands in 1638. Galileo died on January 8, 1942, still officially a prisoner of the Inquisition. But ideas, once unleashed, are harder to imprison than people. The dialogue, despite being banned, circulated in manuscript copies. It was read, discussed, debated. The telescopic observations that Galileo had made were confirmed by other astronomers across Europe. And in Protestant countries, where the authority of the Catholic Church held less sway, the Copernican theory was increasingly accepted by natural philosophers. The Catholic Church itself would eventually, slowly, reluctantly, come around. In 1758, the general prohibition against books advocating heliocentrism was dropped. In 1822, the Church permitted the publication of books treating the Earth's motion as a physical fact, not just a hypothesis. And in 1992, yes, 1992, more than 350 years after the trial, Pope John Paul II formally acknowledged that the Church had been wrong to condemn Galileo, that the judges had unduly transgressed their own limits of competence. The truth took a long time to be officially acknowledged, but it was always true. The Earth was always moving around the sun, whether the Inquisition wanted to believe it or not. Let's rest here for a moment. We've traveled from ancient Babylon to Renaissance Rome. We've watched as humanity slowly, painfully built up its understanding of the cosmos. We've seen observations accumulate, theories proposed and refined, evidence gathered and interpreted. We've seen that the path to truth is not smooth. It's marked by resistance, by honest mistakes, and by institutional inertia, by personal conflicts, and by the difficulty of letting go of ideas that feel intuitively true. But we've also seen that the pursuit of truth continues, that human curiosity is relentless, that each generation builds on the work of the previous one, climbing higher, seeing farther. Galileo pointed a telescope at the sky and saw moons orbiting Jupiter. In doing so, he demonstrated that we are not the center of all things, that the universe is vaster and stranger than we imagined. But he still thought the solar system was essentially the universe. He still thought the stars were distant but relatively nearby, all roughly at the same distance from Earth. He had no idea how wrong he was, how incomprehensibly vast the cosmos really is. To understand that, we need to continue our journey. We need to follow the story forward to a new generation of astronomers, armed with better telescopes, better mathematics, and better physics. And the next major figure in our story was born in the year Galileo died.
Isaac Newton was born on Christmas Day, 1642, by the Julian calendar still used in England, in a small manor house in Woolsthorpe, Lincolnshire. His father had died before his birth. His mother remarried when Isaac was 3, leaving him to be raised by his grandmother. By all accounts, he was a lonely, intense, brilliant child, more interested in building mechanical models and performing mathematical calculations than in playing with other children. He attended Cambridge University, where he initially studied a fairly standard curriculum of ancient Greek philosophy and Aristotelian natural philosophy. But Newton, on his own, began reading the works of the new natural philosophers, Descartes, Galileo, Kepler. And then, in 1665, the plague struck England. Cambridge University closed. Newton, now 22 years old, returned to Woolsthorpe. And there, in enforced isolation during a pandemic, the parallels to our recent experience are hard to miss,
Newton experienced one of the most productive periods of creative thought in the history of science. Later in life, Newton would write about this time. In those days, I was in the prime of my age for invention and minded mathematics and philosophy more than at any time since. During roughly 18 months, Newton developed calculus. Simultaneously and independently, Gottfried Leibniz in Germany was developing the same mathematical system, which would later lead to bitter disputes about priority. Conducted experiments on the nature of light and color, showing that white light is actually composed of all the colors of the rainbow. And most importantly for our story, he began working out the laws of motion and gravitation that would unify terrestrial and celestial mechanics. The story of Newton and the apple is famous, probably too famous. Did an apple really fall and inspire him to think about gravity? Maybe. Newton himself mentioned it late in life, though the story was probably embellished in the retelling. But here's what's important. Newton asked a question that seems obvious in retrospect, but was revolutionary at the time. The same force that makes an apple fall from a tree, could that same force extend all the way to the moon, keeping it in its orbit around Earth? Everyone knew that objects on Earth fall downward. That was terrestrial mechanics, described by Aristotle. Heavy things naturally move towards the center of the Earth. And everyone knew that the planets and moons orbit according to certain mathematical rules that Johannes Kepler had worked out earlier in the century. But these were seen as two completely different phenomena, governed by different principles: terrestrial motion and celestial motion, terrestrial and celestial, different realms, different laws. Newton dared to ask, what if it's all the same? What if one force, one set of laws governs both the falling apple and the orbiting moon? Newton worked out the mathematics. If gravity gets weaker with distance, and specifically if it follows an inverse square law, becoming 4 times weaker when you double the distance, then you could explain both the fall of an apple and the orbit of the moon with the same principle. The moon is falling toward Earth, just like the apple. But the moon is also moving sideways, tangent to Earth, fast enough that as it falls, the curved surface of the Earth falls away beneath it at the same rate, so it's continuously falling but never getting closer. That's what an orbit is, continuous falling around a curve. Newton worked out the mathematics and applied it not just to the Earth and moon, but to the entire solar system. The planets orbit the sun because of gravity. The same force that makes objects fall on Earth extends across the solar system, across the universe, governing the motion of all massive objects. And if you know the mass of 2 objects and the distance between them, you can calculate the gravitational force between them, precisely, mathematically. In 1687, Newton published his magnum opus, Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. The Principia is one of the most important scientific books ever written. In it, Newton laid out the 3 laws of motion, which describe how objects move when forces act upon them, the law of universal gravitation, which describes how all massive objects attract each other, and then using these laws, he explained virtually every known phenomenon in the heavens. Why do the planets orbit the sun? Gravity. Why do those orbits follow Kepler's laws? Because that's what gravity predicts. Why are the orbits elliptical, not circular? Gravity. Why do the tides rise and fall? The moon's gravity pulling on the Earth's oceans. Why does a comet arriving from the depths of the solar system swing around the sun and depart again? Gravity. Why does the Earth bulge slightly at the equator? Because it's rotating, and the centrifugal effect combines with gravity to produce that shape. Newton didn't just explain phenomena, he predicted. He calculated that the Earth should be slightly flattened at the poles due to its rotation, a prediction that was later confirmed by precise measurements. He analyzed the precession of the equinoxes, that slow wobble in Earth's axis, and showed that it resulted from the gravitational pull of the sun and moon on the Earth's equatorial bulge. Most spectacularly, Newton's friend Edmund Halley used Newton's methods to analyze the orbits of comets. Halley showed that a comet observed in 1682 was probably the same comet that had been observed in 1607, 1531, 1456, and even earlier. If he was right, the comet should return around 1758. Halley died in 1742, but on Christmas night 1758, the comet was spotted returning exactly as predicted. It's been called Halley's Comet ever since, and it returns every 75 to 76 years, most recently in 1986. The universe that Newton revealed was fundamentally different from anything that had come before. It was not a cosmos divided into terrestrial and celestial realms with different laws for each. It was not a universe requiring angels or spirits to push the planets along their paths. It was a clockwork, a mechanism, a system governed by mathematical laws that applied everywhere, always, without exception. If you knew the positions and velocities of all objects in the solar system at one moment, you could calculate where they would be at any future moment. The universe was deterministic, predictable, mechanical. This was both thrilling and, to some people, troubling. It was thrilling because it meant the universe was comprehensible, that the human mind, through mathematics and observation, could understand the very mechanisms by which God had built creation. But it was troubling because it seemed to remove God from any active role. If the universe is a perfect clockwork, wound up at the beginning and running according to fixed laws, then what need is there for divine intervention? Where is the room for miracles, for prayer, for providence? Newton himself was deeply religious and grappled with these questions. He believed that God had designed the laws of nature and created the initial conditions, and that the perfection of the cosmic clockwork is itself proof of divine intelligence. But the philosophical implications of his work would continue to reverberate through the centuries, shaping not just science, but theology, philosophy, and our entire understanding of our place in the cosmos. Newton's universe was vast by the standards of his time, but it was still relatively small by ours. The solar system, with its planets orbiting the sun, was understood. The stars were thought to be other suns, probably similar to ours, scattered through space at various distances. But how far away? Were there planets orbiting those distant stars? Were there other solar systems like ours? Was the universe infinite, or did it have an edge? These questions were unanswerable with the technology of Newton's time. The stars were simply too far away, too faint for any telescope of the 17th or 18th century to reveal much detail. But telescopes were getting better, and there were astronomers dedicated to pushing the boundaries of what could be observed. And among them was a man who started his career not as a scientist, but as a musician.
William Herschel was born in Hanover, Germany in 1738. His father was a military musician, and William followed in his footsteps, playing oboe in the Hanoverian Guard Band. But in 1757, the 7 Years' War reached Hanover, and the French occupied the city. The Herschel brothers fled to England, where William established himself as a music teacher and eventually as a church organist in Bath. He was good at it. He made a decent living. By all accounts, he could have had a comfortable career as a musician. But William Herschel had a second passion, astronomy. He read books on optics and astronomy. He decided he wanted a telescope powerful enough to see the heavens more clearly than anyone before him. But good telescopes were expensive, far beyond the means of a church organist. So he decided to build his own. Building a telescope from scratch in the 18th century was not a matter of ordering parts online and assembling them. It meant casting and grinding your own mirrors. Herschel preferred reflecting telescopes, which use mirrors, over refracting telescopes, which use lenses. It meant hours upon hours of grinding and polishing metal surfaces to get them precisely the right curve. Too steep or too shallow by even a tiny amount, and the telescope wouldn't focus properly. It meant trial and error, failed attempts, starting over. Herschel was obsessed. His sister Caroline, who had joined him in England and kept house for him, later wrote about how William would spend 16 hours at a stretch polishing a mirror, with Caroline placing food in his mouth so he wouldn't have to stop and leave the mirror to cool and contract unevenly. But his obsession paid off. Herschel became one of the best telescope makers in England. His telescopes gathered more light and provided clearer images than almost anyone else's.
And he used them not just to look at known objects, but to systematically survey the sky, searching for anything unusual, anything new. On March 13, 1781, Herschel was conducting a routine survey of the stars in the constellation Gemini when he noticed something odd. One star-like object appeared slightly different. It wasn't a point of light like the other stars. It had a small, discernible disk. And when he checked it on subsequent nights, it had moved. At first, Herschel thought it might be a comet, but as he and other astronomers tracked its motion over the following months, it became clear that this wasn't a comet with an elongated orbit. It was something else. It was a planet, a new planet, orbiting the Sun beyond Saturn. No new planet had been discovered in recorded history. The 5 visible to the naked eye, Mercury, Venus, Mars, Jupiter, Saturn, had been known since ancient times. They defined what a planet was. And now there was a 6th. Herschel initially wanted to name it Georgium Sidus, George's star, after King George III, a bit of flattery that earned Herschel a royal pension and the position of court astronomer. But eventually the astronomical community settled on Uranus, continuing the tradition of naming planets after Roman gods. The discovery of Uranus doubled the known size of the solar system. Saturn, previously thought to be the outermost planet, orbits at about 9.5 astronomical units from the Sun. 1 AU is the Earth-Sun distance, about 93 million miles. Uranus orbits at about 19 AU, twice as far out as Saturn. The solar system was suddenly much larger than anyone had realized. And Herschel didn't stop there. He continued his surveys, discovering 2 moons of Uranus and 2 new moons of Saturn. He observed nebulae, those fuzzy patches of light scattered across the sky, cataloging hundreds of them. Some nebulae, Herschel realized, were actually clusters of stars, too distant and too tightly packed for the individual stars to be distinguished without a powerful telescope. The stars were so numerous and so distant that they blended into a hazy glow. But other nebulae remained mysterious. Were they all distant star clusters? Or were some of them something else, perhaps clouds of glowing gas? Herschel suspected the latter, and he was right. We now know that some nebulae are indeed clouds of gas and dust, regions where new stars are forming or where old stars have died and expelled their material back into space. Herschel attempted something audacious. He had tried to map the shape of the Milky Way galaxy. By counting stars in different directions, measuring how densely they were packed, Herschel concluded that the Milky Way was shaped like a disk and that our solar system was somewhere near the center of that disk. His conclusion about the disk shape was correct. His conclusion about our central position was not. We're actually about 2/3 of the way out from the center in a spiral arm. But we couldn't tell that from Herschel's vantage point. The dust and gas in the galactic plane obscures our view, making it difficult to see the galaxy's overall structure from inside it. Still, Herschel's attempt to map the galaxy was pioneering. He was thinking on a new scale, not just the solar system, but the arrangement of stars across vast reaches of space. Herschel died in 1822 at the age of 83, having revolutionized our understanding of the heavens. His son, John Herschel, would continue his work, cataloging nebulae and stars in the southern hemisphere, regions his father had never been able to observe from England. And astronomers across Europe and America were building larger and larger telescopes, pushing deeper into space, photographing the sky, once photographic technology was developed in the mid-19th century, and making discoveries that would have seemed like pure fantasy to earlier generations. They discovered Neptune in 1846 by mathematical prediction. Uranus's orbit was slightly off from what Newton's law of gravity predicted, and astronomers realized that an unseen planet must be tugging on it. Calculations pointed to where Neptune should be, and when astronomers looked there, they found it. They discovered asteroids, small rocky bodies, mostly orbiting between Mars and Jupiter. They began to analyze the light from stars using spectroscopy, splitting starlight into its component colors and reading in those colors the chemical composition, temperature, and even velocity of distant stars. The universe was revealing itself in ever greater detail. But there was still a fundamental question that remained unanswered. Just how big is the universe? How far away are the stars? It's a question that had haunted astronomers for centuries. The ancient Greeks tried to measure stellar distances and failed. The stars showed no observable parallax, which meant they had to be extremely far away, beyond the reach of ancient instruments to measure. Copernicus's heliocentric model actually made the problem worse in a sense. If the Earth orbits the Sun, traveling hundreds of millions of miles in the course of a year, then nearby stars should appear to shift position relative to more distant stars as our perspective changes, just as a nearby tree appears to shift against a distant mountain when you walk past it. But no one could detect this stellar parallax, which meant either A, the Earth wasn't moving, as opponents of Copernicus argued, or B, the stars were so far away that the parallax shift was too small to measure with available instruments. As telescopes improved through the 17th and 18th centuries, astronomers kept looking for parallax, and kept failing to find it. Finally, in 1838, a German astronomer named Friedrich Bessel succeeded. Using a superb telescope and meticulous observation techniques, Bessel measured the parallax of a star called 61 Cygni. The shift was tiny, less than a third of an arcsecond. An arcsecond is 1/3600th of a degree. Imagine taking a degree, dividing it into 60 minutes of arc, then dividing each minute into 60 seconds. That's how small an arcsecond is. And Bessel was measuring a shift of about 0.3 arcseconds. From opposite sides of Earth's orbit, 6 months apart, 61 Cygni appeared to shift by about 0.3 arcseconds. Using this measurement, Bessel calculated that 61 Cygni was about 11 light-years away. 11 light-years. Light travels at 186,000 miles per second, covering about 6 trillion miles in a year. 11 times that distance to reach 61 Cygni. For context, the Sun is about 8 light-minutes away. The nearest planet, Venus at its closest, is a few light-minutes away. Uranus, at the far edge of what was then the known solar system, is a few light-hours away. And the nearest stars are years away at the speed of light. The universe was incomprehensibly larger than anyone had imagined. And 61 Cygni wasn't even particularly far away by stellar standards. It's a nearby star. Most stars visible to the naked eye are tens or hundreds of light-years distant. Some are thousands. This had profound implications. If stars were that far away and yet still visible, they must be incredibly luminous, shining with the power of a sun or even many suns. They weren't little points of light, they were massive balls of burning gas, like our own sun, just unimaginably distant. And if the stars were spread across such vast distances, then the Milky Way, that band of countless stars, must be absolutely enormous. Astronomers began to measure the distances to more and more stars, building up a three-dimensional map of our cosmic neighborhood. The galaxy began to take shape in human understanding. But even as astronomers were mapping the galaxy, a deeper question lurked. What about those nebulae that Herschel and others had cataloged, the fuzzy patches of light scattered across the sky? Were they all part of our galaxy, clouds of gas, clusters of stars, all within the Milky Way? Or could some of them be other galaxies, separate island universes of stars lying far beyond the Milky Way? This question would dominate astronomy in the early 20th century, leading to one of the most famous debates in scientific history. April 26, 1920, Washington, D.C., the Smithsonian Museum of Natural History. Two astronomers, Harlow Shapley and Heber Curtis, are about to engage in what will come to be known as the Great Debate. The question at issue: are the spiral nebulae distant galaxies beyond the Milky Way, or are they smaller objects within our own galaxy? Shapley argued for a large Milky Way galaxy with the nebulae inside it. He based this on observations that seemed to suggest the nebulae weren't very far away. Curtis argued that the nebulae were separate galaxies. He noted that some nebulae showed supernova explosions, and if those were really in our galaxy, they should be much brighter than any star ever observed. But if the nebulae were millions of light-years away, then even an incredibly bright supernova would appear faint. The debate was inconclusive at the time. Both sides had good arguments and some flaws in their reasoning. What was needed was a better way to measure distances, a way to determine how far away the spiral nebulae really were.
Enter Edwin Hubble. Hubble was a complex figure, a lawyer turned astronomer, athletic and charismatic, sometimes described as arrogant, unquestionably brilliant. In the 1920s, he had access to the world's most powerful telescope, the 100-inch Hooker telescope at Mount Wilson Observatory in California, and he used it to settle the Great Debate. Hubble focused on the Andromeda Nebula, one of the largest and brightest of the spiral nebulae. Andromeda is visible to the naked eye on a clear night as a faint, fuzzy patch. Using the 100-inch telescope and long-exposure photography, Hubble resolved individual stars within Andromeda, not just the nebulous glow, but actual stars. And among those stars, he identified Cepheid variables. Cepheid variables are a special type of star that pulses, brightening and dimming in a regular, predictable cycle. Some pulse every few days, others every few weeks. An American astronomer named Henrietta Swan Leavitt had discovered in the 1910s that there's a relationship between a Cepheid's pulsation period and its intrinsic brightness. Longer period Cepheids are intrinsically brighter. This was crucial. If you observe a Cepheid and measure its period, you know how bright it really is. If you measure how bright it appears from Earth, you can calculate how far away it must be to appear that dim. It's like seeing a light bulb in the distance. If you know it's a 100-watt bulb, but it looks very dim, you can figure out how far away it is. Hubble found Cepheids in Andromeda. He measured their periods and their apparent brightness, and he calculated the distance. Andromeda was nearly 1,000,000 light-years away. Modern measurements put it at about 2.5 million light-years, but Hubble's initial calculation was in the right ballpark. 1,000,000 light-years. Far, far beyond anything in our galaxy. Andromeda wasn't a nebula within the Milky Way, it was another galaxy, a separate island universe containing hundreds of billions of stars, lying at an almost incomprehensible distance from us. And if Andromeda was a separate galaxy, so were many of the other spiral nebulae Hubble observed. The universe wasn't just the Milky Way, it was galaxies upon galaxies, scattered through space as far as the most powerful telescopes could see. Hubble identified and cataloged galaxies, classifying them by shape: spiral galaxies like Andromeda and our own Milky Way, elliptical galaxies, irregular galaxies. He estimated that there were millions of galaxies within reach of his telescope. We now know there are at least hundreds of billions of galaxies in the observable universe, possibly trillions. Each galaxy contains millions to trillions of stars. The scale was staggering. And Hubble wasn't done. Working with his colleague Milton Humoson, Hubble analyzed the light from distant galaxies using spectroscopy. Light is made up of different wavelengths, which we perceive as different colors. Red has a longer wavelength than blue. And if a light source is moving away from you, its light waves get stretched out, shifted toward the red end of the spectrum. If it's moving toward you, the waves get compressed, shifted toward the blue. This is called the Doppler effect, and it's the same principle that makes an ambulance siren sound different as it approaches and then moves away from you. Hubble found that light from distant galaxies was red-shifted, shifted toward the red end of the spectrum. The galaxies were moving away from us. Not just a few galaxies, nearly all of them. And the more distant a galaxy was, the faster it was receding. This was extraordinary. It suggested that the universe itself was expanding. Think about it like this. Imagine dots drawn on the surface of a balloon. Now inflate the balloon. As the rubber stretches, the dots move apart from each other. From the perspective of any one dot, all the other dots are moving away, and the farther away a dot is, the faster it's receding. That's what Hubble discovered. The fabric of space itself is expanding, carrying galaxies with it. This had a profound implication. If the universe is expanding now, then in the past, it must have been smaller. Go back far enough, and the entire universe must have been compressed into a much smaller space. Go back far enough, and there must have been a beginning, a moment when the expansion started. This idea would eventually become known as the Big Bang Theory, though that name, originally intended as mocking, wouldn't be coined until decades later. Let's pause again. We've traveled from Galileo pointing a telescope at the moon to Hubble revealing that the universe is expanding.
In the span of just 3 centuries, a blink of an eye in human history, we went from believing that Earth was the center of creation to understanding that Earth is a planet orbiting the Sun is one star among hundreds of billions in a galaxy called the Milky Way is one galaxy among hundreds of billions or more in the observable universe itself is expanding, carrying galaxies apart like raisins in rising bread dough, and the universe had a beginning, some 13.8 billion years ago. It's a journey of progressive displacement. At every stage, we've discovered that we're not as central, not as special as we thought. And yet, paradoxically, each discovery has also revealed how remarkable it is that we're here to make these discoveries at all. We are, as Carl Sagan would later phrase it, a way for the cosmos to know itself.